Okay, so I'm going to talk about, yes. Okay, here I am. All right. So we're really done, finally, with chapter 4, whatever we're going to do in it. And then we're going to sort of move on and cover just a few little things in different sections. So we're actually going to work on these 2 sections of chapter 5. These are the only ones we're going to look at in that chapter. And what chapter 5 deals with is how the Gibbs free energy changes with pressure and temperature. Now, how it changes with pressure is actually more important than you might think, because when we do chemical reactions in the gas phase, as the reaction proceeds, the pressures of the different gases change. So when we study chemical reactions in the gas phase, the pressure gives the amount, right, of each reactant. So this is going to get us into chemical reactions. How the Gibbs free energy changes with temperature is eventually, we're not going to do this right away, but eventually this is going to lead to that Gibbs-Helmholtz equation, which is that log of K2 over K1 equals EA over R, and then the temperature is in there. Remember, I think it was 1 over T2 minus 1 over T1. So that is going to come from the temperature dependence of the Gibbs free energy, believe it or not. I mean, it doesn't look it now, but it actually does. So, so in chapter 5, we're going to start with the definition of the Gibbs free energy. And we're going to then sorry, this is the definition without the D. And then we're going to take the differential, like we often do, of both sides. So we'll have dG is dH minus dTs. And then we're going to do the typical thing that we always do, which is to use the product rule and differentiate term by term. So we'll get TdS and SdT. You've done this before. Let me just check that camera because I'm really bummed by this. Try this again. Yeah, that's it. That's better. Okay. And so then we'll put in the definition of enthalpy. So we'll have du plus PV minus TdS minus SdT. So what we're looking for is an expression for dG that depends only on dP and dt, right? The pressure and temperature. So we're getting there, right? Because the internal energy, this is du plus dPV. It's going to take a little bit. du plus pdV plus vdP minus TdS minus SdT. And now we're going to use the first law. So du is dq plus dw, and then we're going to separate this into expansion work and extra work, and pdv, vdp. Now we're going to start to cancel things. Okay, so we have this whole big thing, and now we're going to say no extra work. Okay, we're going to say that there's mechanical equilibrium between the system and the surroundings. So what does that let me do? So this is minus P external dV. So that allows me to cancel this and this. Oops, wrong one. That one. So now I have that dG is dQ plus, well, I should, that one's gone. And then we have VdP minus TdS minus SdT. And I would dearly love to be able to get rid of these two terms. So how to get rid of these two terms? What would I have to say here? So when do these cancel? Anybody? Remember, dq reversible, ds is dq rev over t, so tds is dq rev. So if the process, if we say reversible, then I have new lights in here too, and they're all like shining right at what I'm writing. I've never done this before. So. Yeah, okay. So if it's reversible, then dq is dq reversible, which is TDS. So I can cancel these if it's reversible. So that's another condition. So far I have 1, 2, and 3 conditions. And then I end up with what I want. dg is VdP minus S dt. Now, this doesn't look like much, okay? but remember back at the very beginning of the term, I said that if you have a function like, say, Gibbs free energy, which is a function of pressure and temperature, right, that dg, the total differential, would be dg dp dp plus dg dt dt. And that this is a completely general expression, right? I'm not telling you what dg/dp is equal to here. I'm just saying that if you have a function of two variables, that the change in that function is how does that function vary with p, with the first variable, times a change in that variable, plus how does that function vary with the second variable, t, times a change in that variable. So this stuff is, this is stuff we talked about at the very beginning of the semester. But now, because we have this relationship here, we can use it, right? We can say that this dg, it's v dp, right? Minus s dt. So that tells you, I'm going to write that way. That tells you that this must equal v, and that this must equal the negative of the entropy, okay? So I'm going to start with looking at this term here, okay? I'm going to say that if the temperature is constant, then I know that the volume is dg dp. Oop, I wrote it wrong. Actually, the temperature doesn't have to be constant. Yeah, I mean, if the temperature is constant, then I don't have this term at all. But this is actually telling us that dg dp at constant t is equal to v. So that's what this means. When you take a partial derivative, you're holding everything else constant. So I don't need to say that. So what is that exactly? So what benefit is this? How is this going to help us at all? Well, first of all, I can say if I write constant temperature, I can make this just a regular derivative. Okay. And then I have dg is vdp. And this is really important because I can integrate this to get to get the change in Gibbs free energy for a process, because the integral of dg, of course, is delta g, you know, between two states, g2 minus g1. So that's one very important thing that I get out of this. But there's another very important, second importance, and that is that I don't have to know how the Gibbs free energy changes or varies with pressure. I don't know how it varies with pressure, but I do know something. I know that the volume is always positive. So I don't exactly know how G depends on P, but I do know that the graph of G versus P has some kind of positive slope because volume is always positive. And I also know that if I'm looking at something happening to a gas, that the volume of a gas is greater than the volume of a liquid. So gases will have greater slopes and liquids and solids will have smaller slopes because they have smaller volumes. You could probably think about this as a molar volume, right? You can't, some's going to have a huge volume if you have a huge amount of it. So for gases, we have larger molar volumes. We have greater slopes. So the slope of G versus P for gases is quite large, and that's because their volumes are large. Here we go. So earlier today, it told me my battery was charged too much, so I took the plug out. Now it's telling me it's low. I can't wait till we run out of power, or I run out of power. Now I have a laptop and no power on, but that's all right. Anyway, now I have this other problem with this computer that I always have. It's all right. God. Wait a minute. This is one thing. So the slope of G versus P is always going to be positive because it equals V, but it's going to be larger for gases because molar volumes are larger and smaller for solids and liquids because their molar volumes are smaller. All right. So what we actually do is we look at this equation. So we're going to work with this thing right here. The dG is equal to VdP. dG equals VdP. And we're going to we're going to integrate this. We're going to integrate it, but we're going to do it with the two cases done separately. So first, we're going to do it for solids and liquids. And then we're going to do it for gases. Okay. So, what we're going to be doing is looking at the dependence of G on P for solids and liquids, and then gases. Okay. So starting with that equation, dG is VdP, solids and liquids. So this is A. Okay, so we're going to integrate this. All right. Well, when you integrate this, you have to think about the volume. Okay, because we're going to be doing this. So here, what about this volume? Does volume depend on pressure? For solids and liquids. So what do we say about liquids? Are we the only ones in the room here, Karen, you and I?
No, Dina's
Oh, no, I
here,
see it.
and looks like Alexis is here as
There's
well.
2 others, though. No, 1 other. Wow. Well, anyway, so does volume depend on pressure for solids and liquids? So the answer to that is no, not really. And the reason for that, right, is because solids, well, liquids are virtually incompressible. We say that they're liquids virtually incompressible and solids really incompressible. So it really doesn't matter pretty much how much pressure you put on a liquid or a solid, its volume doesn't really change. So we can say that this volume is constant. And that makes all the difference, of course, to this integral. Because it means that for solids, we can take this out of the integral. And this is the real reason why we separate solids and liquids from gases when we talk about the dependence of Gibbs free energy on pressure. Okay, so we end up with dg, sorry, the integral of dg. So this, when you integrate this between 2 states, you get the Gibbs free energy difference between those 2 states. I'll tell you what these states represent soon. And this would be integrating from P1 to P2, so just V, P2 minus P1. Okay, now this does not look like an earth-shattering equation. It doesn't even look like it has all that much information in it. But let me tell you what we do with this. So we let G1 equal the standard Gibbs free energy, meaning the Gibbs free energy at the standard pressure of 1 bar. So this is the Gibbs free energy at the standard pressure. Then G2, well, we just call that G. That's the Gibbs free energy at some other pressure that is not the standard pressure. And so going along with this, we let P1 equal that standard pressure, which is 1 bar. Okay, so P0 is just really equal to 1 if we make sure we use bar units. So we have to keep that in mind. And P2, well, that's just P. That's just any pressure that isn't 1 bar. So if you take that and put it in here, what you end up with is G minus G0. So this is the difference between the Gibbs free energy at any pressure. It's gonna be a long day, guys. So instead of having just G2 minus G1, not really representing much, we have G at any pressure, you know, not the standard pressure, minus this is the Gibbs free energy. Should have written that there too. Gibbs free energy at the standard pressure plus V times, now P2 is just P, whatever that pressure is. This is at any pressure, this pressure here, minus P0. So if I take this down again a little bit, do a little bit to it, and I realize that, well, this is really just 1 bar, right? And this pressure has to be in bar. So we end up with G equals G0 plus the volume times the pressure minus 1. P has to be in bar, okay? So what is this? Okay, well, what do we have here? Okay, what this is doing, this is your standard Gibbs free energy at the standard pressure of 1 bar. This is that 1 bar, okay? So this is the difference, the pressure difference, the difference in pressure between the actual pressure of the system and 1 bar. Okay, so if you're right at 1 bar, then this is going to equal 0. And then the Gibbs free energy is just equal to the standard Gibbs free energy, right? So if P is equal to 1 bar, then G equals G0 plus V times 0. And so the Gibbs free energy just equals the standard pressure, or the Gibbs free energy at the standard pressure. Okay, so basically what we have here is that the Gibbs free energy at some pressure that is not 1 bar is that standard Gibbs free energy plus, I call this a kind of a correction term, right? It corrects for, you know, for what the Gibbs free energy should be when the pressure is not 1 bar. But I'd like to talk about this for a minute. Let's talk about the magnitude of V times P minus 1 for a typical situation. Okay, so I'm going to talk about it for, say, a mole of liquid water, right? We're talking about liquids and solids. So what if we have 1 mole of liquid water? Okay, and let's say that that 1 mole of liquid water is held at 2 bar instead of 1 bar. So it's not at atmospheric pressure, which is very close to 1 bar. It's at twice that pressure. So what I want to know is what happens to this term? What is the magnitude of V times P minus 1? So the volume of 1 mole of water, right? That's 18 grams. That's 18 milliliters, right? It's 1 gram per milliliter. So that's 0.018 liters, okay? So V times P minus 1 is going to be 0.018 liters times 2 bar minus 1 bar. So that's 0.0180 liter bar. Well, that's a funny unit, but we know what to do with that unit, right? We can multiply it by 0.08314 liter bar per mole Kelvin over 8.314 joules per mole Kelvin, otherwise known as multiplying by, wait, I did that wrong. Basically, we're going to multiply by 100. Okay, so that comes out to 1.80 joules. So that's the quote correction term to the Gibbs free energy for 1 mole of water when the pressure is 2 bar. Well, that's really pretty minuscule. You know, for doubling the pressure from 1 to 2 bar, we only get a correction of that much, right? That's really very tiny. So we're not going to pay any attention to it, and nobody else is either. And that's why we can just say that it is negligible. And when we do that, it really simplifies things a bit. All right. So that means that since this is so small, right, since this is very small, that G is just about equal to the standard Gibbs free energy for solids and liquids. So we like that. That's nice and easy. So since V times P minus 1 is very small, right? A doubling of the pressure to 2 bar led to a 1.80 joule difference. That's pretty small. So we would just say that G is equal to G0 for solids and liquids. And actually, a lot of times I just write it like, you know, it's approximately equal. It's good enough to be equal. That's how I write it. And if we were to look at the molar Gibbs free energy, we would just take this G divided by the number of moles. And that's, we're just going to say it's equal to G0. So the molar Gibbs free energy is equal to the standard molar Gibbs free energy. So this is the standard molar Gibbs free energy at 1 bar pressure. Okay. So that's what the case is. Very simple for solids and liquids, but as you might imagine, it's a little bit harder for gases because that volume is not independent of pressure. We've integrated things with that volume before, right? So what happens for gases? So this is case B. Okay, so we'll start in the same place. dG equals VdP. We're going to integrate this. Okay. Except now the volume depends on pressure. Okay. So we're going to put that in. And we've integrated this thing a million times, so we really know how to do it. We take the nRT out, temperature is constant. And it's just the natural log, right? The integral of dP over P. But we have to evaluate that, right, from P1 to P2. So this is nRT log of P2 minus P1. And that's our G2 minus G1. And now we're going to do the same thing we did before. We're going to say let G2 equal the Gibbs free energy at any pressure. At any pressure P, okay? That doesn't have to be 1 bar. G1 is the standard Gibbs free energy at 1 bar, okay? So then the left side of this equation becomes the difference between the Gibbs free energy at the when pressure isn't 1 bar and when it is. And so then going along with this, P2 is just the P, any pressure. And P1 has to be that standard pressure of 1 bar. So P0 is just, P1 is actually just 1 in units of bar. So this equation here becomes G minus G0, just like last time, equals nRT log. Now here, P2, we're just going to call that P. And P1, well, that's P0, but that's equal to 1. So if we use bar units, we can just get rid of this. This is equal to 1. So we have to make sure we always use bar units from now on with this. Okay, so we have G, the Gibbs free energy at any pressure is equal to the standard Gibbs free energy at the standard pressure of 1 atmosphere plus nRT log of P. And this is at any pressure, right? This is the Gibbs free energy at any pressure. And the standard pressure doesn't even appear in this formula because it's equal to 1 and we canceled it out. So, so as long as pressure is in bar units, we can use this formula. So don't forget P in bar. So now when we go to look at the molar Gibbs free energy, we're going to divide by N. And you could see that the N's here are going to cancel out. So you'll end up with the molar Gibbs free energy equals the standard molar Gibbs free energy plus RT log of P. So this is the actual pressure in bar, standard molar Gibbs free energy at P equals 1 bar. And this is the molar Gibbs free energy at any pressure. Awful lot of description of what everything means, I know. Everybody hanging on to this? The few people who are here. Okay, Alexis, I see you're here too. Good. All right. So where do we go with this? First of all, I'd like to answer the question, does this make any intuitive sense? Can I do anything to add any, like, belief that this is correct or incorrect to this? So I think I can. I think I can with this situation. So if I have a container, right, and I take a wall, like a movable wall, and I move the movable wall down so that that wall is sitting over here, so that there is no gas here and there is gas down here. And then I hold this wall down with these very sturdy pins. And they have to be very sturdy because I have a vacuum in here, right? So this gas wants to expand. I have the gas, all the gas is down in here. And let's say that I have 1 mole of gas and that the pressure is 1 bar of this gas. Okay, now we know what's going to happen intuitively when we remove these pins. So we remove the pins and the gas expands. The pressure drops, right? It's going to have a greater volume, so the pressure is going to go down. And the container fills spontaneously. Okay. So we know that's going to happen spontaneously. So what does that go along with this equation, which I actually forgot to call this something else? Oh, too bad. I'm going to tell you that now, though. This molar, this symbol that we use for this molar Gibbs free energy, we call it mu. So this is the same equation, except I've used this new symbol to represent the molar Gibbs free energy, and it's called the chemical potential. But right now we're just going to call it the molar Gibbs free energy. So the container fills spontaneously. What's happening with the equation? So you start out with a pressure of 1 bar. And then as this expansion happens, P drops. So as P drops, this term becomes negative, right? And as it does, this mu, this molar Gibbs free energy goes down, right? Because you're adding something negative. Okay, well, at least that makes sense, right? We have something that we know is going to happen spontaneously, which we know that things that are spontaneous processes decrease the Gibbs free energy. We know that expansion occurs spontaneously into a vacuum, and we know that mu drops. So it seems like, you know, if this mu is really a Gibbs free energy, then it should drop, it should go down with a spontaneous process. So it seems like here we have an example. So this is, I'm not expecting a lot of this example. I'm just expecting it to show. So this example shows that for this spontaneous process, GM or mu decreases. So it's consistent with what we've learned about Gibbs free energy before. Okay, so I don't know if that helps a lot, but it's better than nothing. Okay. So this molar Gibbs free energy, this mu, this thing, new variable thing, we call this the chemical potential. And when you have a pure substance, which is what we've been talking about, right? We haven't talked about any mixtures, no reactions yet or anything. We're talking about pure substances. This mu is actually dg dn, the derivative of the Gibbs free energy with respect to moles, if temperature and pressure are held constant. So it's how the Gibbs free energy changes with changing moles of a substance. Okay, so how oh, you know what? Every time I touch this thing, it screws up the microphone because it's a flaky connection. Great, that's just great. All right, whatever. I better not touch that anymore. So let me explain how this works. You know, how is it that why does this work? Okay. So the Gibbs free energy is the number of moles times the molar Gibbs free energy. That's pretty simple, you know, it's just what a molar means. But if we have a pure substance and pressure and temperature are constant, that means that the molar Gibbs free energy is constant. There's no reason why it should change. It's a constant. So this is a constant. So when we take the derivative of this G with respect to the number of moles, we basically have the derivative of a constant times a function, the function being the number of moles. So the derivative is the constant times the derivative of the function. So this is N, right, times the molar Gibbs free energy, GM. So then what we end up with is that we take the constant times the derivative of the moles, which is just 1. So this ends up being the molar Gibbs free energy. So the partial derivative of G with respect to the number of moles, this is for a pure substance. So if you have a pure substance, the Gibbs free energy depends on temperature, pressure, and moles. Okay, but we're holding temperature and pressure constant. And when we do that, this is just the molar Gibbs free energy or the chemical potential. So that's it. So if we have a gas, like we were talking about, we basically have two equivalent. We have the molar Gibbs free energy is a standard molar Gibbs free energy plus RT log of P. And then we just rewrote it. This is the same thing. We have mu, because this is equal to mu. This is the molar Gibbs free energy at any pressure. Same here. This is the chemical potential at any pressure. It's equal. These things are equal. This is the standard molar Gibbs free energy at 1 bar. Okay. This is the chemical potential of pure chemical potential at 1 bar, which is the same thing as a standard molar Gibbs free energy. Of course, it's 1 bar plus RT log of P. Okay, and this is exactly the same. So we're going to use this one because this is the term that's used when we talk about chemical reactions. So what we know is that this is for gases. And if we go back to what we had for solids and liquids, we had Gm equals Gm0. So now we're just going to say, okay, we're going to use the same symbol that we use for gases, this mu. So we say for solids and liquids, the chemical potential is the same. These are all the same definition, but we write it this way. All right, so this is all for pure substances, but we really don't want to talk about pure substances, right? Because we want to talk about mixtures. Because, you know, chemical reactions, they involve mixtures. Right? Most of the time. No, they always involve mixtures. Even if A just decomposes into B, eventually you have a mixture of A and B, right? So this means you need to think about how the Gibbs free energy of a mixture changes when the moles of any one of the components of the mixture changes, because that's what chemical reactions are all about. So we need to think about this. How the Gibbs free energy changes when moles of any one component changes. And so the definition of the chemical potential has to change, right? The definition of the molar Gibbs free energy, if you will, it's going to change when you have mixtures. So we had, this is what we had for pure substances, that mu is dg dn, the derivative, the change in the molar, in the Gibbs free energy, sorry, with respect to moles when temperature and pressure are constant. And so this is for a pure substances. So this is a chemical potential of a pure substance. And it's the same as the molar Gibbs free energy. But now we're going to change our definition. So now to accommodate mixtures, we define the chemical potential of the ith component of the mixture. And that is, instead of, that is a partial derivative But instead of with respect to the moles of the only substance there, it's respect to the moles of the ith substance that's there. Where all the other moles, Nj, those are moles of everything else. Moles of all the other components are held constant. Along with the pressure and temperature. These are also constant. Okay, so now it's a partial derivative, and it looks at how the Gibbs free energy changes. Oops. When moles of only one component changes, right? All right, so this is what we had before. And let me just go over again, right? This is the standard molar Gibbs free energy of a pure substance at 1 bar. That's what this is. This is the actual pressure, which might not be 1 bar. And this is the chemical potential of that pure substance when the pressure is P and not 1 bar. Well, obviously, if it was 1 bar, then these two would be equal and this term would be 0. Okay. So now we have mu I is mu I0 plus RT log of PI. So this is mu I, the new mu I. And these two are actually the same. So that is to say that the standard state, this is the chemical potential of the ith component of the pure ith component of a gas mixture at 1 bar. So it's as if you had just that ith component, the chemical potential of pure I. Let me just call it pure I. Pure gas I in a gas, of pure gas I at 1 bar. So this and this are the same. They're both, 1 bar, that's a standard pressure. Okay, so that's what these two are the same. But now we have here, we have a partial pressure of gas I. Okay, and this is the chemical potential of the ith component of a gas mixture. So here it's like we're taking the chemical potential of a pure substance and relating it to a standard chemical potential when the pressure is 1 bar. Now we're taking the chemical potential of the ith component of a mixture, relating it to, again, the standard chemical potential when that thing is pure at 1 bar. But now the correction has to do with the partial pressure of that component, because it recognizes that there are other components in the mixture which will have their own partial pressures. So this is sort of an important starting point for how chemists, how we deal with mixtures. So I want to actually use it because I don't want to dwell too long on how unfamiliar it is, because I think using it will actually just really help with that. So I want to look at a very simple reaction because I think this will actually, it will actually help. So let me talk about this for a little bit. So suppose we start with all A. I mean, that happens a lot. We start with one, reactants. And let's suppose that PA is initially 1 bar. Okay. So what's going to happen? Well, A is going to react away. So A reacts. The partial pressure of A will drop. Okay. So mu A is mu A 0 plus RT log of PA. Okay, so this started out at 1 bar, but this drops from 1 bar. So this becomes less than 1, this PA. So this term is negative. Okay, so so that means that the chemical potential of A becomes less than what it is initially, right? It drops. CP of A drops as the reaction goes on. Okay, so what about the situation with B? What about the chemical potential of B? Okay, so we have the same general equation. Mu B is mu B 0 plus RT log of PB. And initially, the pressure of B is equal to 0. Well, that makes this, you get an error on your calculator if you try to calculate the log of 0. But what's my point here? Yeah. But certainly, yeah, what does it look like? So what does a log function look like? It looks like this. Wait, that's not right. So this is actually like, it's like negative infinity, right? And as PB increases, the log of PB goes up. So you're like going this way on the curve. Okay. And actually this is 1 here, right? Yeah. Anyway, so the PB is going up as the reaction goes forward. PB goes up, so mu B increases. Okay, it becomes greater than what it was initially. So as the reaction goes on, the chemical potential of A drops. That's the reactant. The chemical potential of B increases. That's the product. Okay, and what happens eventually? So where is equilibrium? Well, it turns out that it's actually when these two things equal each other. But I didn't prove that to you. I'm going to show you more of that later. But what we definitely know about this equilibrium, it happens when the Gibbs free energy is at a minimum. Okay, the total Gibbs free energy is at a minimum, and that actually happens when this is true. But I haven't proven that, but I'm getting there. Okay, so why does it stop when the Gibbs free energy is at a minimum? So we're going along with this reaction. chemical potential of reactants going down. So the Gibbs free energy reactants going down, that product is going up. But at some point, furthering the reaction is going to actually increase the Gibbs free energy total. So we have to figure out where is that point, because at that point, going in either direction isn't going to change the Gibbs free energy. It's not going to decrease it for sure. Okay, we need to always be spontaneous. For a reaction to be spontaneous, go forward spontaneously, it's got to decrease the Gibbs free energy. When it gets to the minimum, it's no longer decreasing. Basically, no more reaction happens. Well, you still get reaction going forward and back, but you don't get any progress one way or the other. So when the Gibbs free energy is at a minimum, this is equilibrium, and there is no further progress in the reaction, either forward or backwards, neither of them. I mean, there's both happening, but they're at equal rates. So let me show you how we get to know this. You know, how do I know this? Okay. And the way I know it is through this crazy thing that I actually showed you at the very beginning of the semester. If the Gibbs free energy is a function of the moles of A, the moles of B, and the temperature and the pressure, then dG is dG dNA, right? The change in moles of change in Gibbs free energy with respect to moles of A times the change in moles of A, plus dG dNB times the change in moles of B, plus dG dt times the change in temperature, plus dG dP times the change in pressure. Okay. In a more general way, this would be the sum of the change in moles, change in Gibbs free energy with respect to moles of all the components, summed over all the components, times the change in moles of each component. And then we would have these other terms here for the temperature and pressure. Okay, so what we're going to do, where we're going with this, is we are going to say that the temperature and pressure are constant. And we're going to deal only with this part of the equation. And this derivative here is known as that chemical potential. So we end up with this equation, that is a change in Gibbs free energy. And I think I'm going to stop here because I don't know, it's so much that everyone who's not here is going to have to catch up on. I just hesitate to do any more. So I'm going to stop here. Yeah. And then I'll come back later for lab.